Hello, my name is Micah Smith. I'm happy to be joining here virtually at CSCW. Today, I'll be summarizing our paper, Enabling Collaborative Data Science Development with the Ballet Framework. And this work is joint with Jürgen Cito, Kelvin and Kalyan Veeramachaneni. So modern machine learning methods are wildly successful in tasks like classification and generation, with structured data like videos and images, where high-quality feature representations of the data can be learned within a deep neural network. However, in many other applications of data science, a primary bottleneck is feature engineering, or the process in which data scientists develop feature definitions, that is, code to transform raw variables in order to input them to a machine learning model. While an idealized feature engineering pipeline is composed of feature functions that are applied in parallel, in practice, data scientists write long scripts in which they iteratively mutate a single data structure. As a result, existing approaches to feature engineering often lead to low-quality software that causes problems in collaborative development settings. For example, feature engineering was a bottleneck in the recent Fragile Families Challenge. This data science challenge asked researchers and data scientists to predict life outcomes, including material hardship and eviction, for a set of disadvantaged children in their families. The complex and unwieldy data led competitors to struggle with data preparation and feature engineering, and to try many differing and often redundant approaches. Instead, collaboration might enable the wide dataset to be processed more effectively and might attract many interested developers with their unique knowledge and insight. Motivated by this setting, in our paper, we explore collaboration in data science development and how it can be better supported through interactive systems, interfaces, and algorithms. More specifically, we focus on collaborative feature engineering and predictive ML modeling. In the first part of our work, we are inspired by successful approaches to collaborative development in traditional software settings, such as the pull request model as exemplified on the social coding site GitHub. We ask, can we support larger collaborations in predictive modeling projects by applying these successful open source software development models? However, we identify several challenges of applying open source development models directly. These include task management, tool and skill mismatch, evaluating contributions, and maintaining infrastructure. We address these challenges by creating 4 corresponding design concepts, which we later instantiate in Ballet, our framework for collaborative open source feature engineering. The first concept is data science patches. We identify steps of the data science process that can be broken down into many patches, or modular source code units. These can be developed and contributed separately in an incremental process. More specifically, we focus on the creation of feature definitions within the process of feature engineering. We also create Assemblée, development environment for feature engineering built on top of Jupyter Lab. The next concept is data science products in open source workflows. The composition of many patches from different collaborators forms a data science product that is stored in an open source repository. In our case, composition of many feature definitions from an executable feature engineering pipeline. The set of feature definitions is grown using pull requests, and Assemblée additionally supports an in-notebook interface for submitting feature definitions without using any low-level version control tools or without exposing these tools to users. We evaluate contributions using the concept of software and statistical acceptance procedures. We create procedures for feature API validation and streaming feature definition selection, which we automatically run in continuous integration environments and give feedback to contributors. In our decentralized model, each collaborator uses their own storage and compute, and we leverage existing community infrastructure for source code management and accepting patches, like GitHub and GitHub Actions. I'll now give you a whirlwind tour of how Ballet supports collaboration in practice for an ongoing collaborative project that we're working on to predict life outcomes for that same Fragile Families Challenge data. Starting from an open source Ballet project repository, we can see that the data scientist in this session has launched our Assemblée development environment by clicking on a badge, and is then using Ballet's interactive client to assist them in loading the data, exploring existing features submitted by their collaborators using an in-notebook feature discovery method, and searching column metadata. Next, when they come up with an idea for a feature definition, they are experimenting in the notebook. Using Ballet's feature definition abstraction, a developer requests some input variables from the raw data, which is the Fragile Families Challenge data, that provides one or more transformer steps that will transform the data, learning subparameters from the development step. According to the in-notebook validation this user is seeing, it has an error. The feature has an error that needs to be fixed, so they are debugging. Finally, we will see that they have created a feature definition that they are satisfied with and that passes validation locally. Now we see how Assemblée supports them in easily contributing their patch back to the shared repository. Under the hood, Assemblée is conducting a static analysis of the code, forking, cloning, creating a new Python module, committing the change, pushing and opening a new pull request that we see at the end. The data scientist does not know that Git is being used at all, but rather has an easy interface to select a small patch from their notebook and contribute it back to the shared repository. I've shared the design concepts that underlie Ballet in a tour of collaboration in action, but for more details on this rich framework, I refer to you to our paper and our software repositories and documentation. In the second part of our work, we ask, can we better understand the opportunities and challenges in large open source data science collaborations? We take advantage of the Ballet framework that we have just created and use it as a technology probe or a research instrument that is deployed to better understand, in our case, collaborative data science. We use a mixed method software engineering case study approach to answer 4 questions. Taken together, we look to better understand humans, source code, and ML modeling in this collaborative project. I'll focus on just 2 of these questions here. In our case study, we focus on the American Community Survey, a source for population and housing information about the US. Our goal in our collaborative project is to predict personal income for survey respondents, which could help optimize administration of the American Community Survey or direct public policy interventions. But the challenge for collaborators is that it is a really dirty data set and badly in need of feature engineering in order to be useful. This is why collaboration is helpful in the first place, to process this wide and dirty data set. We started by using Ballet to create a new project, Predict Census Income. We then invited a diverse sample of software developers, data scientists, researchers, and domain experts in survey data analysis to join the collaborative project. During the research study, participants were asked to complete a task, learn about Ballet, and then contribute a feature definition that helps to predict personal income. During the case study, we collected data from 5 sources, including surveys, source code analysis, and baseline solutions to the problem. In summary, 27 participants completed the case study, of whom 26 submitted a feature and 22 had a feature merged to the shared repository. Importantly, there were 9 participants in our study who had never before contributed to an open source project, and we found that all of them successfully submitted a pull request using our framework. This research question asked, what were the most important aspects of our collaborative framework? Of the functionality in the collaborative framework, in terms of the task of developing feature definitions, participants found that the in-notebook validation and opportunities to learn by example from their collaborators were most important. And then in terms of contributing patches back to the shared repository, the cloud-based workflow demonstrated in Assemblée was far and away the most important aspect. In a qualitative analysis, we identified several themes relating to collaborative framework design: goal clarity, learning by example, distribution of work, and notebook-based workflow. And there are more details on these in the paper. In summary, we found that our new feature definition abstraction, the cloud-based workflow exemplified in Assemblée, and the coordination and learning from referring to shared feature definitions were the aspects that were most important to participants' experiences. And while the concept of data science patches makes significant progress in addressing task management challenges and allowed us to integrate the contributions of 27 people in our case study, frictions remain around goal clarity and division of work to be addressed in future designs. The next research question asks about the comparative performance of a collaborative solution built using Ballet against alternatives. We started by considering end-to-end modeling approaches, such as hiring human data science experts or using commercial automated machine learning systems like Google Cloud AutoML tables. Then we consider, what if we substitute in Ballet's collaboratively generated feature engineering pipeline where appropriate within these alternative modeling approaches? We find that the best ML performance overall comes from using Ballet's feature engineering pipeline together with Google Cloud AutoML tables, and is able to significantly improve the performance of Google Cloud AutoML tables by itself. And this hybrid human AI approach outperforms all alternatives. That's it for our summary of our paper. Thank you for your attention and for joining us at CSCW this year. See you around.